diving deep into the cosmic microwave background.
Okay.
You send over a whole bunch of articles and studies about it.
Right.
And I've always found this just fascinating.
Yeah.
Because it really is like having a direct line to the universe's baby pictures.
Yeah, it is.
So what I'm hoping we can do is kind of sift through all this incredible information
Yeah.
and really kind of pull out the most mind-bending revelations that this CMB has given us.
Yeah, absolutely.
So for anyone listening who might need a refresher,
Yeah.
how would you describe the CMB in like one super concise sentence?
The CMB is the faint afterglow of the Big Bang, a bath of microwave radiation that permeates the entire universe.
Well, okay, cool.
Yeah.
Now, I remember reading about how it was discovered totally by accident.
Oh, yeah.
Tell me that story, and it's just wild.
Yeah, it's a great story. So it was back in the 1960s, and these two guys, Penzias and Robert Wilson at Bell Labs,
Okay.
they were working with this super sensitive antenna, and they kept picking up this persistent hum that they couldn't explain.
Right.
And they went to great lengths to eliminate all possible sources of interference, even cleaning pigeon droppings off the antenna.
Wait, they really thought pigeon droppings were causing a cosmic signal?
Well, they had to rule everything outright.
Yeah.
And in the process, they systematically proved that this hum was coming from every direction in the sky, day and night.
Wow.
They had stumbled onto something much, much bigger.
So that's the moment they realized it was the CMB.
Pretty much, yeah. What they were hearing was the faint echo of the Big Bang,
Wow.
a discovery that won them the Nobel Prize in 1978.
That's incredible.
Yeah.
And what's crazy is that they weren't even looking for it.
Nope.
It just goes to show sometimes the biggest breakthroughs happen when you least expect them.
Absolutely, yeah.
Now, you mentioned baby pictures earlier.
Yeah,
And that's a great analogy.
it is.
The CMB is a snapshot of the universe as it was about 380,000 years after the Big Bang.
Right.
A time when the universe had cooled enough for atoms to form and light to travel freely for the first time.
Exactly.
So we're seeing the universe before stars and galaxies even existed.
You got it.
That's just mind-boggling.
It is, and one of the things that makes the CMB so important is its spectrum.
Okay.
It's incredibly close to what we call a perfect black body spectrum.
Okay, black body spectrum, I remember that term from physics class. But could you give us a quick explanation?
Yeah, sure. So a black body is an idealized object that absorbs all radiation that falls on it and then emits radiation based solely on its temperature.
Okay.
And the CMB's spectrum matches this theoretical black body curve incredibly well, which strongly supports the Big Bang theory.
So the CMB is telling us that the early universe was incredibly hot and dense, just as the Big Bang theory predicts.
Precisely. It's one of the most compelling pieces of evidence we have. But here's where it gets even more interesting. The CMB isn't perfectly uniform.
Okay.
It has these tiny temperature variations or anisotropies across the sky.
Right? I read about those, that they're like these tiny hot and cold spots in the CMB.
Exactly. And these fluctuations, though, tiny, we're talking millions of a degree, are hugely important
Okay.
because they give us clues about the seeds of structure in the universe.
Okay, hold on. What do temperature fluctuations have to do with the formation of galaxies?
Okay.
I explained, like, I'm 5 because I think this is where my brain starts to melt a little.
Okay, sure. So imagine the early universe as this nearly uniform soup of matter and energy.
Okay.
These tiny temperature variations in the CMB represent areas where the density of matter was slightly higher or lower than average.
Oh?
Over billions of years, gravity acted on these density differences, pulling more matter into the slightly denser regions. Those regions became the seeds for the formation of galaxies and all the large-scale structure we see in the universe today.
So those tiny temperature differences in the CMB are basically the reason we have galaxies, stars, and planets.
Yeah, pretty much.
That's just wow.
It really is remarkable. And by studying the detailed patterns of these fluctuations, cosmologists can learn about the composition of the universe, its age, and even test theories about what happened in the first fractions of a second after the Big Bang.
Okay, so we've got the accidental discovery, the black body spectrum confirming the Big Bang, and these tiny temperature variations that led to everything we see around us.
Right.
What else is the CMB hiding?
Well, the CMB has helped us determine some pretty fundamental things about the universe.
Yeah.
For example, it helped us pin down the universe's age to about 13.8 billion years.
I've always wondered, how do we get that number from the CMB?
It's a combination of factors. So the patterns in the CMB tell us how long it took for the universe to cool down to its current state. That, along with measurements of the expansion rate of the universe, lets us calculate the age pretty accurately.
So it's like a cosmic clock ticking away since the very beginning.
Precisely. And the CMB also tells us about the universe's composition.
Okay.
Remember those ingredients we talked about earlier?
Yeah.
The CMB data reveals that normal matter, the stuff we're made of, only makes up about 4.9% of the universe.
Right. The rest is dark matter and dark energy. Those mysterious entities we can't directly see.
Exactly. The CMB provides some of the strongest evidence for the existence of dark matter and dark energy, even though we still don't fully understand what they are.
Okay, so we've got the age, the composition, anything else?
The CMB also provides support for a mind-blowing concept called cosmic inflation.
Okay.
The idea that the universe underwent a period of extremely rapid expansion in the first fraction of a second after the Big Bang.
Yeah, inflation. I remember reading about that.
Yeah.
Didn't solve some problems with the Big Bang Theory?
Yes. One of the puzzles the Big Bang Theory couldn't explain is why the universe is so uniform on large scales.
Right.
Regions of space billions of light years apart have almost the same temperature. That's hard to explain unless they were once in contact with each other. Inflation solves this by proposing that the universe expanded incredibly fast, very early on, smoothing out any initial variations and making those distant regions causally connected in the past.
So, inflation is like a cosmic ironing board, smoothing out the wrinkles in the fabric of space-time.
That's a great way to put it. And while we still don't have definitive proof of inflation, the patterns in the CMB strongly suggest that something like it must have happened.
Wow, okay, so accidental discovery evidence for the Big Bang, insights into the universe's age composition and support for inflation. The CMB has given us a lot to chew on.
Right.
So is there anything else we should touch on before we move on?
Well, there's one more thing. Remember the Hubble tension we discussed earlier?
Yes.
The discrepancy between different measurements of the universe's expansion rate.
Yeah, how could I forget? It's like this nagging mystery hanging over cosmology.
Right. And the CMB plays a role in that, too. One way to measure the expansion rate is to use the CMB as a sort of yardstick.
How does that work?
By analyzing the patterns in the CMB, we can extrapolate back in time to figure out the universe's expansion rate at the time the CMB was emitted.
Okay.
That gives us one value for the Hubble constant. But other methods, using observations of nearby objects, give us a slightly different value.
And that's the heart of the tension.
Yeah.
Right. Two different methods giving us two different answers.
Exactly. It could be a problem with our measurements, or it could point to some new physics we don't yet understand. It's an area of active research, and who knows, maybe the CMB holds the key to solving this puzzle as well.
It's incredible to think that this faint signal from the early universe has given us so much information and so many questions to ponder.
It truly is a cosmic treasure trove, and we've only just begun to scratch the surface of what it can teach us about the universe.
Yeah, it's amazing to think about how much information we've gleaned from the CMB.
Yeah.
And yet it raises just as many questions, right?
Totally. I mean, we've talked about how the CMB supports the Big Bang theory.
Right.
But I'm curious, are there alternative theories out there about the origin of the universe?
That try to explain the CMB in a different way.
That's a great question, and it gets to the heart of the scientific process. There have been other theories proposed, sure, but none have been able to explain the properties of the CMB as elegantly and comprehensively as the Big Bang model.
Yeah.
The Big Bang theory, with the addition of inflation, really does the best job at accounting for what we observe.
So the Big Bang with inflation remains the reigning champion, at least for now.
Yeah.
But I'm sure scientists are still exploring all the possibilities, right?
Absolutely. That's the beauty of science.
Yeah.
It's a constantly evolving process.
Right.
New data can challenge existing theories, leading to refinements or even entirely new paradigms.
Speaking of challenging theories, we were talking about the Hubble tension earlier.
Right.
What are some of the ideas out there for resolving this discrepancy?
Yeah.
Could it mean we need to modify our understanding of gravity or even consider new fundamental forces?
There are quite a few proposals on the table.
Yeah.
Some more exotic than others. Right. One possibility is that there's something we don't fully understand about dark energy or dark matter.
Okay.
Maybe their properties change over time or interact with each other in ways we haven't accounted for.
So those mysterious entities could be even more complex than we thought.
It's possible. Another idea involves modifying our theory of gravity.
Okay.
Einstein's theory of general relativity has passed every test thrown at it,
Mm-hmm.
but it's possible that it needs some tweaks at very large scales or under extreme conditions.
Tweaking Einstein's theory, that's a pretty bold move.
It is.
But Hey, if that's what it takes to explain the observations, then scientists have to go where the evidence leads.
Exactly. Some researchers are exploring the idea of modified gravity theories,
Okay.
which tweak general relativity in subtle ways to see if they can account for the Hubble tension without disrupting the successes of the standard model.
Are there any frontrunners among these modified gravity theories?
Um,
Or is it still a wide open field?
it's still early days. There are a few contenders that have shown some promise, but none have emerged as a clear favorite. It will likely take more data and theoretical work to determine if modified gravity is the solution or if we need to look elsewhere.
Okay, so dark energy, dark matter, modified gravity.
Hmm.
What other wild ideas are cosmologists tossing around to solve this cosmic puzzle?
Well, there's a whole class of theories known as early dark energy models.
Okay.
These propose that there was an additional form of dark energy present in the early universe that influenced the expansion rate back then, but has since decayed away.
Early dark energy. So even more dark energy than we thought. It's like the universe's way of saying, hey, you think you're starting to understand me? Think again.
Right. The universe loves to keep us on our toes. But what's exciting is that these different possibilities make specific predictions about what we should observe in the CMB and other cosmological data.
So the CMB is not just a window to the past, it's also a testing ground for our theories about the universe.
Exactly. By studying the CMB in more detail, especially its polarization,
Yeah.
we can potentially distinguish between these different explanations for the Hubble tension.
Polarization. We touched on that earlier, but I don't think we really explained what it is.
Right.
Give us a quick rundown.
Sure. Think of light as a wave. Light waves can vibrate in different directions.
Mm-hmm.
When they vibrate in a specific direction, we say the light is polarized. Now, the CMB light was polarized when it interacted with electrons in the early universe.
Okay.
By measuring the polarization of the CMB, we can learn even more about the conditions in the early universe and potentially detect the signature of primordial gravitational waves.
Primordial gravitational waves.
Yeah.
Those are the ripples in space-time generated by inflation.
Right, got it. Detecting these waves in the CMB would be a smoking gun for inflation and give us a direct glimpse into the universe's first moments.
Wow. So the CMB could hold the key to unlocking some of the biggest mysteries in cosmology, from the nature of dark energy to the validity of inflation.
It really could, and that's why researchers are so focused on studying the CMB with ever-increasing precision. There are new telescopes and instruments coming online that will give us even more detailed maps of the CMB,
Wow.
potentially revealing subtle features we haven't seen before.
I'm getting the sense that the story of the CMB is far from over.
Yeah.
Like every new discovery opens up a whole new chapter in our understanding of the universe.
I couldn't agree more. The CMB has revolutionized cosmology, and I have no doubt that it will continue to surprise us for years to come.
Well, I think we've done a pretty good job of unpacking the CMB's secrets.
Yeah.
We've covered its discovery, its connection to the Big Bang, the information it gives us about the universe's age and composition, its role in supporting inflation, and even how it might hold the key to resolving the Hubble tension.
Right.
What else is there to explore?
Well, one thing we haven't touched on is the connection between the CMB and the formation of the first stars and galaxies.
Okay.
Remember those tiny temperature fluctuations we talked about?
Yep.
They not only seeded the large-scale structure of the universe, but they also played a crucial role in the formation of the first stars.
Okay, so how did that work? I'm all ears.
Well, after the universe cooled enough for atoms to form, it entered a period known as the cosmic dark ages.
Okay.
There were no stars or galaxies, yet just vast clouds of neutral hydrogen gas.
Right.
But within those clouds, gravity was slowly pulling matter together, guided by the subtle density variations imprinted in the CMB.
So those tiny temperature variations were shaping the universe even during the Dark Ages.
Yes. They acted as gravitational wells, pulling in more and more matter. Eventually, these clouds of gas became dense enough for nuclear fusion to ignite, giving birth to the first stars.
So the first stars were born from the seeds planted by the CMB. That's a beautiful thought.
It is, and those first stars were quite different from the stars we see today.
Okay.
They were massive, hot, and lived short lives, ending in spectacular supernova explosions.
And those supernovae, didn't they play a role in enriching the universe with heavier elements?
Exactly. The first stars fused hydrogen and helium into heavier elements, like carbon, oxygen, and iron. When they exploded as supernovae, they scattered these elements into space, providing the building blocks for the next generation of stars and planets.
It's amazing to think about how this cosmic chain of events all the way from the Big Bang to the formation of the first stars, has shaped the universe we see today.
Yeah.
And it all started with those tiny whispers in the CMB.
It's a remarkable story, and it highlights how interconnected everything is in the cosmos.
Yeah.
The CMB isn't just some distant signal from the past, it's woven into the fabric of our existence.
It's truly humbling, and I have a feeling this is just the beginning of our journey of understanding the CMB and its profound implications. It really is mind-blowing to consider how those first stars forged from the remnants of the Big Bang set the stage for everything that followed.
Yeah, it really underscores how interconnected the cosmos is. The echoes of the Big Bang are still shaping the universe we see today, from the largest galaxy clusters to the very elements that make up our bodies.
Whenever I think about the CMB, I can't help but wonder about the future.
Yeah.
I mean, what will happen to this cosmic signal as the universe continues to expand and evolve?
That's a fascinating question. As the universe expands, the CMB photons are getting stretched out, their wavelengths getting longer, and their energy decreasing. This means the CMB is actually cooling down over time.
So billions of years from now, will the CMB fade away completely?
It's possible. Eventually, the CMB might become so faint and stretched out that it will be undetectable with even the most sensitive instruments. It'll be like a whisper lost in the vastness of space.
That's kind of sad, but I guess it's inevitable. But hey, maybe then we'll have discovered some new cosmic signal, something even more ancient and mysterious than the CMB.
You never know what the universe might have in store for us. That's what makes cosmology so exciting. There's always something new to discover, something that can challenge our understanding and push the boundaries of human knowledge.
I think we've done a pretty good job of diving deep into the CMB today. We've talked about its discovery, its significance for cosmology, the mysteries it's helped us solve, and the even bigger mysteries it's revealed. So anything else you think we should highlight before we wrap up?
Well, I think it's worth emphasizing that the study of the CMB is a global effort. Scientists from all over the world are collaborating on projects to map the CMB in ever greater detail, analyze the data, and develop new theoretical models to explain what we see. It's a testament to the power of human curiosity and our collective desire to understand the universe we inhabit.
Yeah, it's inspiring to think about all those brilliant minds working together to unlock the secrets of the cosmos. And who knows what groundbreaking discoveries await us in the years to come. Maybe we'll finally solve the Hubble tension, detect those elusive primordial gravitational waves, or uncover something entirely unexpected.
The possibilities are endless. The CMB has shown us that the universe is a truly remarkable place full of wonder and complexity. And it's a reminder that we're part of something much larger than ourselves. A cosmic story that began almost 14 billion years ago and continues to unfold to this day.
Well said. And on that note, I think it's time to wrap up this deep dive. It's been an incredible journey exploring the wonders of the cosmic microwave background, and I'm sure I speak for our listeners when I say that we've come away with a renewed sense of awe and a deeper appreciation for the vastness and mystery of the universe. Thanks for taking us on this cosmic adventure.
It's been my pleasure.
And to our listeners, thanks for joining us on this deep dive into the cosmic microwave background. We hope you found it illuminating, thought-provoking, and maybe even a little mind-bending. Until next time, keep exploring, keep questioning, and keep looking up at the stars.